Hello and welcome to the next episode of compiler programming. Last time we created a bunch of these functions that encode individual x64 instructions with a particular set of operands. And I mentioned that it would be really nice if we didn't have to create a separate function for each one of those encoding and instead have something more general. So today we are going to try to do something like this. We will not obviously get all the way, but just get some head start. And in particular, I will focus on trying to encode this instruction in a more generic way. So what I'm imagining is would be nice if I have something like I pass so asymmetric reserved keyword, so I can't use that. Let's just say we'll have function instruction and I pass the identifier of the or mnemonic, which is like move. Then I would have the registers, so RCX and RAX. So this something like this is what I would like to have. Since C does not really have variable, it has variable arguments, so maybe we can do like this, maybe, or we encode into mov that it knows that it needs two operands. That could work, and then we can use var args in C to kind of nicely represent. It actually might be really neat if we can make it work. Or we could alternatively we could actually sort of implement even like this, RCX, RAX, right? And that would give us back, or more likely we need to provide the buffer, which is slightly annoying, but it's fine. So I'm not sure what exactly it will look like, but something along those lines. But first, we need to understand what will be the general way to encode the instructions, and to that we need to look at the format of those instructions. Let's open up our compiler explorer stuff, and I remember if I right click here, yeah, I can do codes, and I can go to here. Great. So this page shows me all the variants of the instruction, and this let me quickly talk you through what all of this actually means. I will ignore compatibility legacy mode. I don't think we will be dealing with this at all, so just for now we can ignore this this column. This means, I believe, operator / encoding, but I'm not sure. I do know what these two-letter combinations mean. So if you have MR, then that means that the first operand is either register or memory, and the second operator is register. So basically they took in like M stands for memory and R stands for register. And if we look at this line, it actually says RM, which is reverse. And if we look at the instruction definition, it is indeed reverse. So first comes the register operand, and then comes the register or memory operand. The opcode column is the most straightforward one, probably, except for this weird /R, and in some cases you have this plus, or you have, I'm not sure if for example, you also have this /0 here. So what does it mean? This first part is literally the main opcode, and /R refers to the fact that because there are two operands here, this operand actually goes into particular part of the instruction. And to make it more visual, I found this really nice page, which I'll link in the description, that kind of showcases you the structure of the instruction. We will mostly ignore the optional prefixes for now, except for rex prefix, which I will talk about later. But for now, we can just, so if I undock this here, and we have this side by side somehow. So maybe make this smaller. Yes, like this. So this opcode goes into here. And as you can see, it can be 1 or 2 bytes. For now, like the move instruction, I believe only has 1 byte variant. So this is what we will focus on. And then comes this byte, or optional byte, that is called mod-rm. And mode literally means mode. And rm is register or memory. This byte consists of 3 parts: the mode part, register or opcode part, and register memory, which tells us if we are referring to register or to specific memory. This /r is this register or opcode part. So if it says /r, that means we put register here. And if we look down here, where it says C6/0 or C7/0, that means that we are putting 0 into these 3 bits. And as I mentioned, RM refers to one of the operands. I will not talk about SIB byte for now. Let me just say that SIB refers to scaled index byte, and the bits are scale, index is the register contains index base is what we are computing from. I guess I'm talking about SIB. So SIB is used basically when you have an array and you want to go through that array. So we'll have to do it at some point, but it's not important right now. Displacement is necessary when we're dealing with memory. So once we get to encoding one of those instructions that has to deal, for example, with stack, like what we did last time, we will have to care about displacement, but for now it will be 0 for the instruction that I chose to start with. And immediate is, for us, is also 0, but what it is if we look at our code, like when we have, for example, we have add RSP immediate 8. So we are adding this byte, and as you can see, we put it last, and this is exactly corresponds to this part of the instruction. Once you kind of get this picture in your head, it's looking at the instruction becomes a bit easier, but it still takes a bit of getting used to this model, and I still make lots of mistakes. We will need to use the mode reg_rm today, and in particular, we will use this mode equal to 1,1, where we address 2 registers. So as we go back to the instructions we want, we have 2 registers. So this needs to refer to register addressing mode. And we'll also need to transcribe this table into our application somehow. This particular page deals only with x86, not with full x64 architecture. So it actually doesn't have the full registers. So don't kind of, this only describes 32-bit version of this, but it is accurate to 32 bits. With 64, you have more registers, and there are some weird things that you, for example, can't address. I believe these versions like AHBH and so on. Okay. This we will also need to use this table at some point, but I think today we can just skip it for now. And this is cbyte. So like this page is really good. As I said, I will link it in the description. So if you want to dive deeper, you can do that. But for now, let's just start. And I like to start usually with some kind of data types. So what we will need to have, we will need to have a concept of an operand, which is which will be either immediate, or it will be some location in memory, or it will be a register. And as I said, for today, we only care about the register option, but it's nice to put some scaffolding for future so we can easily extend the application that we have. So let's say that we have type def enum, and we will call it operand type, and this operand type will be register for now. Let's not overcomplicate our life and do register. And yeah, most of the time I like to start enums with one that are not indicating some kind of presence or absence of value. So because it's in C, you can very easily initialize memory to 0, and if you do that, you can have some accidental uninitialized stuff interpreted by something you didn't want. So just starting this with 1 and having an assertion later that it's not 0, it helps to make sure to catch bugs that are connected to uninitialized memory. Obviously, in this language, I would like to have much better options to deal with that, but for now we are in C, so this is what we have to do. Great. We have operand type, and we also need to have sort of the register struct. Register would have it's basically just a wrapper type. It will be literally U8 of register, and I can't use register, so I use reg, because register is a keyword in C. So we have register here, and we need kind of now more global operand struct that will be either register or other types that I mentioned. If you worked with something like Rust or Haskell or whatever, where you have some types, basically in C you can represent some types, but it's a bit annoying to do so. Nevertheless, this is how we're going to do it. So, and we say this is operand. Great. Now we have operand. We need to have type here, or operand type, and we now will have a union. So just in case you don't know, if you have this kind of anonymous union inside of a struct in C, it allows you to access it straight on the main struct, which is quite handy instead of an extra field, because you could also put like a field in here. Okay, union, and we have reg or register reg. Great. And here, maybe we should call it index. Cool. Now we need to have the registers themselves. And we have this, first of all, let me try to build it. Okay, fine. We have this handy table here, which tells us what is the name of the register and what is its index. So we can start to create, I think like we can create straight up globals for this register operand, so it's much more handy to deal with them. Const operand arrayx is, what is it? So dot type is operand type register, and then register is const register of index, and I like to use binary here because the register follows a certain pattern, and it is actually important what is this bit versus these 3 bits, and it's just easy for me to think like in binary rather than hexadecimal about this. Okay, so let's see if this is something we can even do. What does it say? Initializer is not constant. Is it not? I mean, I can also make it non-constant, I guess. Doesn't really matter. We are not thinking about performance. Initializer is not constant. I guess it doesn't like this stuff. What do I do it this way? Oh, okay. So actually can put it back to being constant. Right. Didn't know that, but I'm learning as well. Cool. We have racks, and I will not create all of them. I will just create the ones we need for now, and I will probably like fill in this whole table of videos so we don't have to sit and through me copy pasting a bunch of values. And RCX is 0001. The reason here it's only 3 bits and I have 4 is, as I said, because this page is about x86 and x64 is an extension which has sort of 1 more bit to represent registers. Great. So we have our operands, and now we can. Yeah, we also will need, I guess, these constants, which is mode and friends. Okay, so let's define those. Should I do this as an enum? I guess I should. Type def enum mod. So mode displacement 0. And this one we can actually leave as 0. Displacement 8 and displacement 32. Or actually, I'll even do it like this. S8 and S32. Because this is what it says. 1 byte sign displacement and 4 byte sign displacement. And yeah, we will not go into what is register indirect addressing or displacement only mode because it's a longer topic and not important for now. And the last one is mod register. Great. So this is 0B00, 0B01, 0B10, and finally 0B11. Good, good, good. What else do we need? We will need, let me dump this back into here. We also need to know what this rex w rex means and what are the values for those. I think I can literally just search for rex w, and probably this is definitely not what I'm looking for. Intel instruction set PDF sounds great. Yeah, so there is this official PDF instruction from Intel that lists all the information about all the instructions, different addressing modes, quirks, everything that you need to know. It is not light reading at all, but it should include the information about our favorite Rex byte. Thing is, I need to find this now. If I remember correctly, this is not so far from the top. This is basically the same picture as we saw here, so you can also refer to this one. And it says the Rex prefix is optional and must be right before opcode. Rex prefixes. Great. Encoding. Yes, great. This is what I've been looking for. And this is a very funky diagram of how all of this works. Okay, let's encode this. So we have now Rex, and there is just Rex, and it will unfortunately collide with an enum name. So I'd say Rex byte will be the name of the enum, but here I prefer to have shorter names because we will use these values quite a bit. And the basic Rex thing is, I believe, like this. So this is what it says. So bit position 7 to 4 is these 4 bits. And then we have 4 bits of zeros. It's really unfortunate that C does not have this separator. C++ does now, but C doesn't still. So dealing with bits is a bit tricky. Anyway, we have Rex, we have Rex W, we have Rex R, Rex X, and Rex B. Out of these, the only one we'll care about is Rex W, and I can sort of copy paste these comments so we don't forget what this means. And same for this, and this, and this. Great. Still need to put the actual values though. So they are for some reason in reverse order. So this is actually like this, because it says bit position. And if you look at this big bit pattern, so now you can see that it's actually quite regular. If we bring out the calculator and go to programming one, then we can do, so remember that 48, if we look at what looks like in binary, it is 100, so 0, 100, 1000, and this is exactly this Rex W prefix that I mentioned before. Great. So we now have this. And instead we, for now, will ignore X and B, I believe. Extension of modern. Yeah, we don't need this. Good. So let's try to build again. Builds fine. And now we want to actually start encoding stuff. So the question is, what would instruction encoding actually return? We can make it more efficient but less nice to use by passing the buffer to whatever we'll be encoding, or it can actually return as a fixed size array, because I believe there is a maximum size for the instruction, like it can only be so many bytes, but I'm not sure. Like we can basically try to combine all of this and see what will be the maximum size. It's also written somewhere in this document, I just don't remember where. I guess let's make it efficient and maybe we use some macro to hide the buffer argument. Okay. What will be the signature of our function? Say void encode. It will accept something that is, I guess, instruction, and it will also, as we said, will accept the buffer. And do we need anything else? No, not really. Okay. So now we actually need another type which will represent the instruction. And by instruction, I mean something like this, right? So we need to represent this in a data structure. For that, we need the mnemonic, and we want to encode the instruction. Let's say type def struct. What will it have? It will have so I guess we'll need an enum for the mnemonics. So x64 mnemonic, and here we will do map. Let's just start using these raw ones, and then if it collides with something, we'll fix it. For now, map, and here we don't really care what the value of it is, I guess. But again, let's start with 1, so we don't accidentally have it initialized. Type def enum. I guess we could also here make 0 interrupt 3 or something, which we'll see what it does later. But it's kind of a nothing or of the instructions. Type def struct instruction. We'll have x64 mnemonic, and then we have arguments or operands. I believe instruction cannot even have more than 3 operands, but for now we don't even have that. We only have 2, so let's just say we have 2 operands. So operand 1, and then operand 2. Probably also do it like this. Operands 2. Yeah, that also works. Okay, we have mnemonic and we have two operands. I think that's all we need for now. So let's try to see how it will look like. We have this instruction, and instead of doing this, we'll say encode buffer and then const. Let me do it here. Instruction is like this. Actually, I don't want this to be an array because it will be a bit awkward to work with in other places, I guess, or not. Yeah, let's keep it an array. We by default initialize everything to 0 and then initialize separate fields. So we have mnemonic, which is mav. If you really want to, we can do it in line, which kind of will look nice. So we have mav, and then we have array. We have two arguments, and this is exactly copying from here, rcx, arrayx. Code buffer, and maybe even let's inline it like this. Instruction. This even looks pretty neat, if you don't mind me saying so. Okay, code buffer actions. So this should build if I can fix the problems. Buffer. Yeah, doesn't know what buffer is. So let's put buffer up. Right. Now if we try to run though, it's either gonna crash or just fail. I'm not sure which one. Yeah. Great. So we have two tests that are making use of this move to RCX from arrayx. And now obviously this encoding function doesn't do anything. So let's make it do stuff. For that to happen, we also need to tell our application, like, so far we encoded basically parts of this picture of like how its instruction structured, but the second part of it, we now need to tell our code this part, like all of the different combinations of operands that the instruction can take and what will be the encoding of that. Right now we will not take, not obviously implement all of them, but just take one that we were using, which we can look up by the opcode. So this was 4889, 4889. This was this version of the instruction. So we need to somehow encode this into our types as well. Let's do that. So we'll need type def. Let's call it encoding. Let's go here. Type def struct or instruction encoding. It needs to have an opcode, as it mentions here. So we can more or less look at this as well. It's either 1 or 2 bytes of opcode. It's why I used U16 instead of just a single byte. And we will need to deal with that later. Anyway, okay, opcode. Then we have we somehow need to encode this /r/0 or another version which is like immediate byte. No. Well, let's just call it instruction extension, I guess. So type def enum instruction extension type, and we have either a register or we have code. Or we have, I'm not even sure how to call this, to be honest. Basically what this means is you take the opcode byte and you add the register bits directly to that opcode. So I guess opcode plus register. I don't know. Code plus register. Sounds fine. And here maybe I'll call it opcode extension. No, opcode is fine. Either maybe call it plus register. Doesn't matter for now. Okay, so we have the type, but in case where it is an opcode, we will also need to have the value. For now, I guess it doesn't really matter, so we'll keep it as it is and just put this instruction extension type into here. Extension type. Okay, actually, maybe how is it called here? Opcode. This is expansion prefix. Do they call this somehow? Cannot see that. I think this should at some point explain how those things are called. Instruction prefixes. Okay, maybe I will do this as stream and try to find what is the right terminology for this part of the opcode. So we now have a kind of a very basic struct for instruction encoding, and it also needs to have an allowed array of operands, but they also might be missing somehow, so we'll need to take into account that as well. And for now, I guess we will say that operand types, operand types. Sounds good. So this is just need to add this. Yep. This is a struct that describes one encoding, but we need to actually create one. I guess let's start with just hard coding it and saying that our instruction encoding is what? Opcode is, now we can use this table. There is similar table here as well. Let me show you. So we need move instruction, and there are a lot of different variants of move, and this is kind of gives you roughly an idea of what is the most prevalent variation that you can have in your program. It is moving memory from one place to another, to register, to memory, with repeating, without repeating, with various sizes, prefixes, and so on and so forth. Like even this page, I think by far is the longest. It is the longest table they have. Well, maybe I'm wrong, but it's definitely one of the longest. Okay, this is our rex w plus 89.3. It's a bit easier to copy paste it from here, so I'll look at this version, which is basically exactly the same. So that means that our opcode is 0x89, and our extension. Is this how you spell extension? No, it's not. It's extension. Is it though? Sometimes I'm really bad at English. It is extension. So I misspelled it here. Extension type is, for us, it is register. And operand types are this. This register memory 64 and register 64. So we can't actually use, we can't actually use the same type here, unfortunately, because when we are dealing with an actual value, we know that it's either register or it is a memory, but for encoding purposes, it can be either one of them. So we will need to have like operand encoding type, I guess. Operand encoding. Should I just call it operand encoding? Not operand encoding type. Operand encoding type. Type def in operand encoding type. This is a lot of kind of boilerplate before we get to actual encoding, but this is necessary because this part will also get more and more complicated, and we need to have a nice scaffolding for that. Operand encoding type. I believe we don't need to specify 64, 32, or 16, but we will need to specify 8 as a separate thing, because if you look here, 64, 32, and 16 versions, they all actually have the same opcode. So this is sort of the standard version. This will have rex prefix, and this will have 16-bit prefix. But if we're talking just about bytes, then we do need to have a special version for that. And I think it is like this for all the instructions. But for now, we maybe don't even need the 8-bit version separately anyway. So operand encoding type, should I call it RM, or more explicitly register memory? I think I will call it explicitly register memory. And another one that we will need is just register. Maybe switch them around. Register and register memory. Okay. And getting back to our table, so operand types, One of them is, the first one is register memory, and the second one will be register. Good. See if that works. Operand types is not a member. Operand encoding types. I also need to do this, otherwise it will be angry at me. So this just tells compiler, yes, I know encoding is not actually used in this function. But now we will use it. So great, we have this instruction encoding struct that just takes this information here and encodes it into a struct. Time to make use of it. How will that look like? So the first part is we need to sort of make sure that the instruction that is passed to us actually matches what we wanted to encode. But I guess for now we can just say that we should do that and instead assume that it does. So let me check that encoding matches the instruction. And another fix me here is that this should be some kind of lookup table. Should be lookup. Great. For now, we manually make sure they match, so we don't need to do this. But we will need to actually do the encoding. If we look at this operand, besides the type, it also ideally needs to know the size. So like this, so we can choose the right version here. For now, we will just assume that the size is always 64-bit and add another fix me. Fix me adds rex w prefix only if necessary. For now, we just assume it is always like that. So we say we just take buffer. I say buffer. Guess I need to move this functions a bit up to the buffer. Otherwise, we can call them. I think in next video or maybe off stream, I will also start splitting a bit this file so it is easier to deal with and it's not so long and hairy to work with. And also buffer is obviously a separate thing that can live in its own file. Buffer append append is I8 or is it U8? It's U8. Append U8 buffer, and we just say rex v. Right? Next thing after rex, it comes opcode, and we need another fix me here that says if actually this one we can probably let's do a fix me. If opcode is 2 bytes, need different append. For now, we just do append U8 of buffer and then encoding opcode. Let's see. Okay. And actually, it correctly complains to us that Well, you told me in definition that it can be 2 bytes, but you're trying to append this as 1. So fix me is definitely in order. Cool. We have rexw, we have our opcode. The only thing remaining is the mode rm portion of this instruction. And this is where we need to do a bit of bit shifts to make it work. So modes rm byte, let's just say that it's 0. What does it consist of? Actually, we can do it probably like this. First, we need to have our mode byte, mode 2 bits. So this is a thing that we're looking for: mode, register or opcode, and register memory. In our case, it will be mode, register, and register memory. And this is exactly what we're gonna do. And as always, even more fix me. Implement proper mode support. For now, we just take mode register and we need to shift it by 6 bits. As you can see, it takes bit 6 and 7. So we're shifting it by 6 bits. We need to OR that with our register. So this will be instruction, operands, operands 0 dot, what do we call it? Rec dot rec dot index. Rec dot index. And this will need to move by 3 bits, as you can see here. So let's do that. And finally, we have the register memory part, which is very similar to the register part. It's basically just taking the second operand and putting it in the right place. And here we do not need to do any shift. In reality, we will need to do some additional masking here, but again, later. For now, we just want to make this part work. Let me mask register index. Okay, so we have our mod rm byte, and we want to append that thing as well. Mod rm. Great. Let's see how much it explodes. Syntax error, syntax error. Ah, yeah. Oh. It doesn't even explode. So we have exactly the same functionality as we had before. So instead of even having this function, we can get rid of it. And replace it with the more generic version. What don't you like? Yeah, like this. So it's better. Yes, it's better. And then encode. Cool. So let's recap what we did today. We looked at the instruction format for x86 and x64. We kind of transcribed some of the constants and enumerations and types that we will need to have to allow us to easily encode this format, and created the formatting routine that only works for our very specific purpose. I guess that will be it for this video. As I said, between the episodes, I will probably fill in some of the tables so we don't have to do that much copy pasting, but I will try not to do any kind of proper development work, so you can see that live in the video. With that, thank you so much, and see you next time.